Hello friends, in this video we are now going to learn about geometrical isomerism. Now let's try to understand what is isomerism, isomers. So isomers are those having same molecular formula but different structure. So those are called as isomers. So what about the geometrical then? Geometrical is a kind of measurement. So in more clearly to say, it is about the relative arrangement. So relative arrangement of atoms or groups around something. So here let's try to understand very clearly with some examples what are isomers as well, which are called as geometrical isomers, and what are the conditions behind to be called as geometrical isomers. Now let's try to take the example of difluoroethane. Now I am showing the structure as here. So I can also write this as CH2, CH2, F and F. It is nothing but difluoroethane. Now I can also show with a different structure. Hope you are following. The same thing I am writing with each element and with dashes. So parallelly also I am taking one more example, difluoroethene. So let's try to understand clearly with these examples which are called as isomers and actually what are called as geometrical isomers. Now let us see here. So here if you observe, both of these having the same formula. Now here it has C2, H4, F2. So the same composition is present in both these pairs, in both of these pair. So it is satisfying the condition that same molecular formula but different structure. So now this can be called as isomers. So similar case can be also applied here. So here we can say it as C2, H2, F2. So both are having the same molecular formula but different arrangement. So these are also called as isomers. Now where the difference is arising then, that is relative arrangement of atoms or groups. Here we can see atoms or groups are relatively arranged in a different direction. Now if you observe here, these two fluorines are arranged on the same side. When coming to this case, they are being arranged in the opposite direction. So this kind of arrangement, so aligning on the same side we call it as cis and opposite we call it as trans. So cis and trans presence is the sure to be identified as isomers. So between a pair we should have certain difference like cis and trans, so that we can identify those two are a pair of isomers. So here also the same case appears. These two fluorines are on the same side or same side of alignment, and these are on opposite side, therefore these are called as cis and trans respectively. So up to here it is very clear that they have same molecular formula but different structure. The different structure is because of the relative arrangement of atoms or groups. Once in case of cis, that is aligning on the same side, and other case of trans aligning on the opposite sides. So up to here it is very clear. Now among these, can we call both of these as geometrical isomers? No. So what makes the difference then? Now let us try to look out what are the checkpoints to be called as geometrical isomers. Now have a glance at here. So when we call it as geometrical isomers, so there should be a difference in spatial arrangement of groups or atoms, that is presence of cis and trans. Next, restricted rotation of atoms or groups, that is they should not be interconvertible. So that can be attained by the presence of pi bond, or atoms on the same carbon should be different. Now let us try to identify in these examples. Now what the first point says, difference in the spatial arrangement of groups or atoms, that is presence of cis and trans. So both in cases, so in the first example difluoroethane, so I write it here very clearly, difluoroethane, and here difluoroethene. So in case of difluoroethane, it is satisfying the first condition, difference in spatial arrangement of groups or atoms, that is presence of cis and trans. The same case is also been applied for the difluoroethene also. Here also cis and trans. Now with the first checkpoint, it is not enough to identify which are geometrical isomers. Now let's move to the second point. So what is the next checkpoint? That is restricted rotation of atoms or groups, or else they should not be interconvertible. Now if you observe here, in case of difluoroethane, here there is a presence of sigma bond between these two carbon atoms. So between these two carbon atoms there is a sigma bond. So sigma bond, obviously it allows a free rotation. So a free rotation, whereas here between these two carbon atoms, in case of difluoroethane, so there is a presence of pi bond. So as there is a pi bond, there is a restricted rotation. That means in case of difluoroethane, there is a free rotation, whereas difluoroethane, there is a restricted rotation. Whatever second checkpoint will say, restricted rotation of atoms or groups. So difluoroethane satisfies the second condition. First condition is satisfied by both, but second condition is satisfied only by difluoroethane. So by this we can clearly say that difluoroethane is a geometrical isomer pair, whereas difluoroethane is not a geometrical isomer. So, and also we can also clearly understand they are to be called as geometrical isomer, they should not be interconvertible. Now let's take a case of difluoroethane. See, there may be a case like, so this fluorine can also rotate and come up here, is it? So as there is a free rotation here, so it can come upside or freely rotate, and both becomes cis as well as cis. When both are cis, there is no difference in the structures. So what to be called as isomers, they should have a different structure. As there is a free rotation, they can come to this position. This F can move up, or else this F can move down. Both can become trans, or in this case both can become cis. So they are interconvertible. Those isomers which are interconvertible are called as conformers. So instead of calling as geometrical isomers, these can be called as conformers. So here, because of presence of pi bond, there is a restricted rotation. Therefore these are called as geometrical isomers. Now there is also even third checkpoint to make it very strong. The presence of geometrical isomers is that atoms on the same carbon should be different. Now if you see here, this carbon is also not just having the fluorine on it, so it also has hydrogen. So even this carbon is also having one hydrogen as well one fluorine. So in this way it is following the three checkpoints to be called as geometrical isomers. Now look at few examples. Now here fluorobromoethene. So both of these structures. Now what were the checkpoints? Let us try out with our checkpoints. What is our first checkpoint? Difference in spatial arrangements of groups or atoms. So here both the atoms, so fluorine and bromine, if you observe these two, if you are selecting fluorine and bromine, they are on the same side, is it? Or else you can also take the hydrogen. So both the hydrogen are on the same side, so therefore they are called as cis. Now coming to this case, here hydrogens are at different orientation, so spatially their spatial arrangement is different. So as the spatial arrangement is different, we can call it is satisfying the first point, checkpoint. Next, restricted rotation. It is known that there is a presence of double bond which does not allow the free rotation. So restricted rotation, therefore they can be called as geometrical isomers. So these are the first example stands for geometrical isomers. Now let's try out with the second example. Now here if you observe, here chlorine and here chlorine, is it? And here also if you observe, they are in what orientation? They are in a trans orientation, whereas here these are also trans, but the way of what we are viewing in a different direction. Our view is in a different direction, but however both the structures are same. So being the structure same, they are no more called as isomers. So these are not the geometrical isomers. Now let's move with the third example. Now here if you look, fluorine is making a cis with this first chlorine and making a orientation of trans with the second chlorine. Is it? It's very clear. Now if you observe here, even this fluorine is making cis with one chlorine and trans with the other chlorine. Leave out what is the first or second. But what is the case here? The fluorine is making cis orientation with one chlorine and trans orientation with the other chlorine. The same is being repeated in the other structure. So as both are having the same structure, as there is no difference, so they are no more called as isomers. So therefore these are not the geometrical isomers. Now let's try out with the fourth example. Now if you observe here, so to this carbon and to this carbon, so what is there? So one side it is methyl and it is methyl and it is a ethyl. So here also ethyl and methyl. So both the ethyl groups are one side, so this is a cis. Even here methyl, this is also cis. Whereas here this ethyl is to one side and this ethyl to the opposite side. So here it is a trans. So cis and trans, different spatial arrangement. Second checkpoint, restricted rotation because of double bond or pi bond. So it is a geometrical isomer. And also if you go for the third checkpoint, atoms on the same carbon should be different. Are they different or not? One is having ethyl, one other group is being methyl. So both are not equal here. Even here also not equal. So if both are equal, then they are no more called as geometrical isomers. So friends, I hope you like this video. Please subscribe, share and like. Thank you.